Hello, it's Miss Adams from Flamingo Math. This is Lesson 11, the first day. We're going to talk about equivalent representations of both polynomial and rational expressions. Our goal is going to be to fine-tune all the techniques for analyzing graphs of rational functions. We can use factoring techniques, and that will help us find the zeros, the domain, and other important features of a polynomial or rational function. In example 1, we want to write an equivalent representation of the function to be able to use that equivalent representation and find features that we could use to sketch the graph. So thinking about factoring, if we factor out the greatest common factor of x, that leaves a polynomial of x squared minus 2x minus 15. That can be further simplified as the product of x minus 5 times x plus 3. Using those factors, we know that the function has zeros at 0, at 5, and at negative 3. So thinking about that and the fact that it's a positive 1x cubed, we know that the graph is going to start low and snake around and end high. So it's going to have that cubic look. This 3 zeros, one at negative 3, the graph is going to go up, come back down, and then another at positive 5. So 3 zeros, the end behavior is down on the left and up on the right. So we can use techniques throughout the unit based on our knowledge to create graphs. In example 2, we want to write an equation for f of x that's in factored form and determine the values of x where the function has a whole or a vertical asymptote. So factoring and simplifying, the numerator can be simplified to be x plus 4 and x minus 4. The denominator, we're looking for factors of negative 28 that add up to be positive 3. That would be x plus 7 and x minus 4. Removing the common factor, we have that simplified. So now we know that there is a whole where x is 4, and substituting 4 up here, you get 8. Substituting 4 down here, you get 11. So 8 over 11 is the y-coordinate for the whole. And then lastly, the vertical asymptote is where the denominator is 0. That would be negative 7. Moving on to example 3. If you're given the rational function at right, can you analyze and graph that function? If you feel brave and you've got this, you can turn the video off and try on your own. If you need more practice, you can work with me. We want to write the equivalent form. So if you factor the numerator, we have x plus 4 times x plus 3, and the denominator is x minus 2 times x plus 3. The x plus 3 factors can be removed, and that would let us know that we have a 0 when x is negative 4. So we can come over here and put a little dot there. There's a whole located when x is negative 3, and if you substitute negative 3 here, that's a 1, and substitute negative 3 here, that would give us negative 1/5. So negative 1/5 is the y-coordinate for the whole. That's going to be really close to the x-axis there. Another important feature, if you substitute 0 everywhere, 12 divided by -6 leaves 0, -2. So that could give us one more point. Let's see, what else can we do? We can know, looking at the leading coefficients here, x squared over x squared leaves y equals 1 for the horizontal asymptote. So we've got y equals 1. And the vertical asymptote is going to happen where the denominator is 0. So that's x equals 2. I've got x equals 2 is a vertical asymptote. Y equals 1 is a horizontal asymptote. We know the behavior of the graph over here because we can see ordered pairs. Now our last piece of information is, where does the rest of the graph go? Is it up here or is it down there? So one way we can determine that is simply to pick an x value on the other side of the vertical asymptote. So let's give it a try with 3. If we substitute 3 here and 3 here, that's going to be 7 over 1. So when x is 3, y is 7. That tells me the remaining branch of the graph is going to come around there in quadrant 2. And then finding the domain, so we read the graph from left to right, starting at -infinity to -3. That's where the hole is located. On the other side of -3, we go to 2. That's the vertical asymptote. And then from 2 to infinity. So putting everything together from the entire chapter so far, we're able to completely analyze rational functions. Are you ready to go backwards? So given the graph of the function at right, you want to be able to write an equation in factored form. Knowing this, let's see what we know. We've got a hole at x equals 4, so the numerator and the denominator have a common factor, x minus 4. So we know that. Got to have x minus 4 in the top, as well as the denominator, because those would be eliminated. What else do we know? X equals 2 is a vertical asymptote, so x minus 2 is a common factor. And we have y equals 1 is a horizontal asymptote. So if y equals 1, we could have, let's see, we've got a 0. We got a 0 at -3, so x plus 3 is a factor in the numerator. And if we canceled these two out, the simplified form would be plus 3 divided by x minus 2. And let's see, what would the whole be located at? 4. So 7 over 2. This ordered pair would be 4 and 3.5. And I believe we've done that. So if we wanted to write that equation in factored form, it would look like this step right here. In the last lesson, we found how we could find a hole in the graph if common factors canceled out. But in this lesson, we're going to explore what happens when the common factors have different degrees, either in the numerator or the denominator. We saw a little bit of that in the earlier lesson. We want to clarify whether we would have a hole or a vertical asymptote, and how would you be sure? So consider the function f of x here. We want to write an equation in factored form, find any of the values where the graph would have a hole, a vertical asymptote, or a horizontal asymptote. The first thing we want to do is factor completely. So factoring out x out of the numerator gives us x squared plus 2. And x squared is already factored out of the denominator. we can take the x out of the top and reduce the x in the bottom. So we're ending up with x squared plus 2 divided by x times x minus 3. So let's make some notes about what we know. We know that the factors are larger in the denominator. On that x over x squared. So we know x equals 0 is a vertical asymptote. Second, we know that x minus 3 equals 0, so x equals 3 is a vertical asymptote. A third thing we know is we have x cubed over, and I'm looking back here, x cubed with some other stuff. So that tells us the powers are the same and the ratio is 1, so y equals 1 is the horizontal asymptote. Let's look at part B and see if we can determine the features of that. So it looks like you can eliminate the x plus 3 in the bottom and one of those in the top. What happens when the factors are larger in the numerator? Factors are larger in the numerator. What does that tell us? That negative 3 is going to be a hole in the graph. We also know that x minus 2 in the numerator is going to give us a 0 at x equals 2. And lastly, we also know that x plus 1 in the denominator is going to give us a vertical asymptote at x equals negative 1. Are you able to make a conclusion about the behavior of the common factors and the degrees of the factors related to their position in the rational function, whether it's the numerator or denominator? See if you can come up with a list before we move forward. Here's my understanding. I hope you agree with that finding as well. Let's move on to look at slant asymptotes one more time. A slant or oblique asymptote occurs when the degree of the numerator is 1 degree higher than the degree in the denominator. The slant asymptote is the quotient polynomial that's found by using long division. Let's think about the division algorithm. We know that if we divide by numbers, let's look at the next example. 675 divided by 21. 675 is our divisor. 21 is our dividend. 21 divides 67 3 times. That's 63. When we subtract, we get 4 and bring down the 5. 21 divides 45 2 times. 21 times 2 is 42, and that leaves 3. So we have a quotient, that's 32, a remainder, that's 3, and our answer is 32 and 3 over 21, which is also 32 and 1/7. We've already seen earlier that we could do the same thing with polynomials. 2x plus 1 divides 6x squared plus 7x plus 5. 3x times 2x is 6x squared, and 3x times 1 is 3x. When we subtract the next line, 7 minus 3 is 4 x's. Bring down the 5 and repeat that process. 2x divides 4x 2 times. 2 times 2x is 2x, and 2 times 1 is 2, and then we subtract. 4x minus 4x, I'm sorry, I wrote that down incorrectly. This is a 4, is 0, and 5 minus 2 is 3. So our quotient becomes 3x plus 2, which would be the slant asymptote. Remainder is 3, and using the division algorithm, which I didn't dwell on, but it's stated up here, this is the division algorithm, your answer, your dividend, is equal to the quotient times the divisor plus the remainder. So we could write it in that format. The dividend, which is 6x squared, 6x squared plus 7x plus 5 is equal to the quotient times the divisor plus the remainder. For example 6, we want to find the equations for any asymptotes to the graph. So first we'll start with factored form. G of x can be factored as x times x plus 5 times x minus 2. And the denominator can be factored as x plus 5 times x plus 3. Removing those common factors is going to give us a simplified factored form of x times x minus 2 divided by x plus 3. The vertical asymptote comes from the denominator. There is no horizontal asymptote, and we need to use long division for finding the slant asymptote. So I'm going to use the simplified form right here, this portion, and say that x plus 3 is my divisor, divides x squared minus 2x, I distributed this, plus 0, and x goes into x squared, x times x squared plus 3x. We're going to subtract those first two terms. That's negative 5x, and bring down the 0, and minus 5 for my quotient. X times negative 5 is negative 5x, and minus 15. And then when we subtract, we're going to ignore the remainder. The quotient is by expression for the slant asymptote. In example 7, we're looking at where horizontal asymptotes come from. So this should be pretty straightforward. 3x is less than x squared. The horizontal asymptote is y equals 0. In part B, 5x squared is the same as 2x squared, so we want the ratio of the a number divided by the b number. The horizontal asymptote is 5 over 2. In part C, the numerator power is exactly 1 larger than the denominator, so we would want to perform division, long division. We need a placeholder for the x term. There is no x term. It's just like having a 0 in a number. 2x divides 4x squared 2x times. So 2x times 2x plus 1 is 4x squared plus 2x. We're subtracting and bringing down the negative 8. 2x goes into negative 2x, negative 1 time. And we really don't have to continue because we have our answer here. Y equals 2x minus 1. This is our slant asymptote. So we have a slant on this one, where this had a horizontal and this had a horizontal. And part D, we've got 6x to the 0 power here. So x to the 0 is smaller than x squared. That means the x-axis is our horizontal asymptote. In example 8, we want to sketch the graph of a rational function that has the properties listed here. Looking through those properties, it appears to be that there is a horizontal asymptote at y equals 2. So we got that from this statement. There is a vertical asymptote, it looks like, at -3. I got that from this statement here, -3 from the left and the right, unbounded behavior up and down. So we could go put the -3 here is our vertical, and 2 is the horizontal. What else do we know? When x is undefined at 5, the y value at 5 is heading to 3. So what do we know about the ordered pair 5, 3? That would be a whole. So when x is 5, y is 3. Seems like the graph is going to go here in this branch, and then it's got to be down here. It's got to approach 2 as we go unbounded. That's to the left here, and it's got to go down when we go to 3 from the left. So all kinds of clues. You just put the clues together, and we have a really good representation of that rational function. And then lastly, there's a procedure on the next page that tells you step by step, if you need to come back to this as a reference for how to analyze the graph of a rational function. We've been looking at this over the last 3 or 4 videos. Example 9 kind of has us work through completely that concept in the procedures. I'm looking at r of x, trying to factor that. So x minus 5 times x plus 4, taking out an x in the bottom and thinking of factors of 12 that add up to 1 would be plus 4 and minus 3. And removing those common factors, we have the simplified form for r of x as x minus 5 in the numerator, and then x times x minus 3 in the denominator. Our zeros come from the numerator, so 5, 0. There's a whole where we took the common factor out at -4. You'd need to substitute that in. I did that on the calculator and got about 0.321 for my r of -4. The vertical asymptotes come from the denominator, so that would be at 0 and at 3. The horizontal asymptotes come from the powers and the leading coefficient, so y equals 0. And let's get the graph first, and we'll figure out the domain after we're finished. Drawing in our vertical asymptotes, 1 at 0 and 1 at 3. A horizontal asymptote at 0, that's the x-axis across here. And we know that there's a hole in the graph at -4 and a little fraction, so we've got the graph going to go here, this way. Now, how do we find out what's going on in the middle section and in the far right section? So one way to do that would be to substitute in, I like to do it this way, think about at 0, 3, and 5. So we know there's a hole here at -4 and 0.321. You know, there's a hole there, but this behavior turned out to be below the axis, so we drew that section over here. but what happens in the middle and what happens to the right. So one way to do that is to substitute a number. This was does not exist, this was does not exist, and this was a 0. So substitute a number in here, and we got a positive value by plugging in, let's say, put a 1 here, and a 1 here, and a 1 here in our R of x expression back here. Put a 1, and a 1 for that area is positive. Put a 4 here, here, and here, and you get negative in that region, and then something bigger than 5, and we get a positive. So following the behavior, we don't have to know numbers, we just know that it's up here somewhere, so it's got to curve around and stay within the boundaries of the vertical asymptote. We know 5 is 0, and here's a little trick. You may have been told that you can't cross a horizontal asymptote, but that's not entirely true. In this case, you do cross the horizontal asymptote at 5, 0, and the graph stays very close to the horizontal asymptote as the values get larger and larger. I believe that's the end of this first lesson.